Hello everyone, welcome to the channel. In this video, we will see a problem on analysis of beam element using direct element matrix equation. Okay, the question says that using directly the element matrix equation for beam element, analyze the beam shown in the figure completely. Okay, so we have a figure and it's a beam element and they have given the given data as well. They have given F0 here it's nothing but the UDL load. Okay, if you see the figure, it is a UDL load, uniform distributed load. Okay, and it is 1 kilonewton per meter. UDL is 1 kilonewton per meter and it is equivalent to 1 Newton per mm as well. So kilonewton per meter is equivalent to Newton per mm. They have given the length of the element. So we have two elements. The length of the element is 5 meter. So make a note, it is in meter. So we have to convert into mm because all other units are in mm. And they have given the Young's modulus as well for both the elements E1 and E2 equal to 2 into 10 power 5 Newton per mm square. And they have given I, that is a moment of inertia as well, 2 into 10 power 7 mm power 4, and I2 for the second element it is 1 into 10 power 7 mm power 4. Okay, so these are the given data. So we have to analyze the beam completely. Okay, so first of all, I'll just draw the line diagram for this. If you see the line diagram, it is nothing but the replication of the exact diagram in terms of line. So here, this is the first node. It is a fixed node. In the third node, it is a hinge support. Here they have given the support. So we have two elements. So this is our first element. This is our first element. And this is our second element. And the nodes are first node, second node, and third node. The length of the elements are 5 meter each. Okay, so in the second element, we have a load of UDL. So it is a UDL load. Fine. So in beam element, each node will have two deflections. In beam element, will have a deflections. Okay, so we have a deflection and slope. Each node will have a deflection and slope. So this can be written in the terms of, first of all, I'll just give the numbering. Numbering for beam element will be 1, 2. Second node will be 3, 4. And third node will be 5, 6. So if you see, the numberings are continuous. Okay, 1, 2, 3, 4, and 5, 6. So as I mentioned that in beam element, each node will have deflection and forces. So this can be written as in terms of deflection and slope. So W1, W2, and W3, W4, W5, W6. So this is the deflection and slope. So this represents deflection and slope. Deflection and slope. So in terms of forces, we'll have two forces. One is shear force. Here I'm just giving the notation as Q1 and Q2. So we have a shear force and bending moment. So this could be Q3, Q4, Q5, Q6. So this represent, the Q term represents shear force and bending moments. So if you see in beam element, we have to find 4 parameters. One is deflection, slope, shear force, and bending moment. So these are the 4 parameters we have to find. Okay, now which number represent deflection, which number represent slope, and which number represent shear force, and which number represent bending moment. So here the even numbers, let's start with the even numbers of W. That means W2, W4 and W6. This represents slopes. This represents slopes. Okay, and similar manner, odd numbers of W, that means W1 comma W3 comma W5, this represent deflection. Okay, and similar manner for the forces as well, even number of Q. Okay, so this is the Q, that is Q2, Q4 and Q6. So this represent bending moments. And the odd number of Qs, represent the shear force. The floor is a shear force. Q1, Q3 and Q5. This represents shear force. Okay, so before getting into the beam problem, you should know all these parameters. So in beam problem, we'll have 2 degree of freedom, that is 1, 2, 3, 4 and 5, 6. And we have to find 4 parameters, that is deflection, slope, shear force and bending moment. They have given all the parameters. W1, W2, W3, W4, W5, W6 represent the deflection and slope. All the W's represent deflection and slope. All the Q's represent shear force and bending moment. So now I'm going to do deep. So even number of W represent slopes, odd number of W represent deflection, even number of Q represent bending moment, even number of Q represent, odd number of Q represent shear force. Okay, now I hope you understood this numbering. Now we'll solve with the formula first. So element matrix equation for beam element. Okay, so it starts with 2EI. E is the Young's modulus, I is the moment of inertia, 2EI divided by L cube. So L is nothing but the length of the element. And since we have a 2 degree of freedom, so each node will have 2 degree of freedom. So it will be a 4 by 4 matrix. So it starts with 6 minus 3L minus 6 and minus 3L. So the second row, it is minus 3L. Then we have minus 3L. We have 2L square, 3L, then L square. Third row we have minus 6, 3L, then 6, then 3L. Okay, so now the last row, that is minus 3L, L square. Here we have 3L, then the last one is a 2L square. So this complete the stiffness, this thing. Then this is multiplied with the deflection slope matrix. So here we have taken deflection as W, deflection slope. So W1, W2, W3 and W4. So this equals to the load matrix. Since we have a UDL loading as well, so the formula for UDL will be F into L divided by 12 into, this represent the 6 minus L, 6 and L, plus the shear force and bending moment, that represent Q. So Q1, Q2, Q3 and Q4. So this is the element matrix equation. So here this represents the stiffness matrix. Okay, so this represents the deflection slope, and slope multiply this deflection slope, that is a deformation. So this represent UDL loading. Okay, this represent the UDL loading factor, UDL loading matrix, and this represent the shear force and bending moment. Okay, So now what we are going to do is we are going to divide the element into two parts, and we are going to find out the each parameters. So first I'll draw the diagram again over here. So these are first node, second node, third node, first element, second element, and w1 comma w2, w3 comma w4, w5 comma w6. So here we have a UDL. Okay, so the element 1 EME will be element matrix equation. We have to find the first parameter 2E1 I1 divided by L cube. So L cube is nothing but the element 1 length. So it's 2 into E1 is they have given in the problem, E1 is 2 into 10 power 5 mm per square. Okay, 2 into 10 power 5 Newton per mm power mm square. Then the moment of inertia for the first element is 2 into 10 power 7 divided by the length is 5 meter. They have given the 5 meter, we have to take in the mm, so it is 5000 cube. Okay, so if you do the calculation, we will get as 64 Newton per mm. Okay, so in the problem they have given that 1 kilonewton equal to meter. So 1 kilonewton per meter is equal to 1 Newton per mm, right? So here we have Newton per mm, so I can write down this as 64 kilonewton per meter. Okay, now we can put it in the equation format. So element matrix equation for the first element would be, here we have 64 into, so it starts with 6, so 6 and 3 into 5, because 5 element, it's minus 15, it's a meter, so minus 6 and minus 15. We have to multiply the elements, so minus 15, then 50, 15, 25, then we have minus 6, 15, 6 and 15, then minus 15, 25, 15 and 50. See, so here it's nothing but we have to multiply the length over here. So here if you see the diagrams, if you see the formula as well, so here this is the diagonal of the matrices is positive and it's a positive value. And if you see, this is a symmetric value. See here we have a minus 3L, again minus 3L, minus 6, minus L, so minus 6 and L, so minus 6 and 3L, minus 3L, L square L, minus 3L, L square L. So it is kind of a symmetric matrix. Okay, it's easy to memorize as well. Okay, so I have multiplied those values again into, since we are dealing with the first element, it will be like, here we will have first element numberings are W1, W2, W3 and W4. This will be equal to, now in the first element, do we have any UDL load over here? In the first element, we don't have any UDL load. So here F will become 0. So here the UDL will become 0. Okay, so since it is 0, this term, the UDL term will become 0. So we have only the forces term, that is Q1, Q2, Q3 and Q4. This is the bending moment and shear force, this thing. So I'll give the numbering. If you see the first element is lying between 1, 2, 3, 4. Okay, so the numbering would be 1, 2, 3, 4, 2, 3 and 4. So this is the first element. Now similarly for the element 2, for element 2 again the same formula we can apply. So 2E2 I2 divided by L2 cube. Okay, so here 2 into 10 power 5, the same Young's modulus. I2 is 1 into 10 power 7 mm power 4 divided by, it's in meter cube, so it will be 5000 cube mm cubes. So this gives me the value of 32 Newton per mm. So again, I'm taking this as a 32 kilonewton per meter. Okay, I'm taking the in terms of per meter. Now you can again put the values in the matrices. So 32 will be taken outside. You have to multiply with those values. So it starts with 6 minus 15, 3 into 5 minus 15, 3L. Again minus 6 minus 3L. Then we have again minus 3L, that is minus 15. Then we have L square, sorry, 2L square, I guess. Yeah, we have 2L square. So it will be L is 5 into 25 into 2, it's 50. Then we have 3L, 15. Then we have 25 L square. So again, it's a replica of the symmetrics, minus 6, 15. Then here we have 6, then 15, then minus 15, 25, 15 and 50. So this is the Strickland matrix for the second element. So now we have to multiply this with the second element numbering. The second element is lying between this 3, 4, 5, 6. So we have to multiply with those deflection and slope. W3, W4, W5 and W6. So here we have to check for the UDL as well, right? So because if you see here we have a UDL load, we see we have a UDL load. So the UDL load F0 is given as 1 kilonewton per meter. Okay, they have given it in terms of meter. So what we can do is we can take is a minus. So because F is acting downward, so it will be minus 1. So here formula was F into L divided by 12 into 6 minus L, 6 and L. So this plus addition of the shear force and bending moment, addition of the shear force and bending moment. It starts with Q3, Q4, Q5 and Q6. Since we have this F load as well, we have to multiply those values as well. So I'll just what I'll do, I'll just find out the value of here only. So F is 1 into L is 5, this is minus and 12. So if you put it in the calculator, we'll get the value as 5 divided by 3 will get as this is equal to minus 1.67. Okay, so minus 1.67, this will be minus 1.67. 1.67 and inside we have minus L and L, so it will be 5 minus 5 and 5. Now what we have to do is we have to multiply those values, and what I'm going to do is I'm going to, if now we have to add both the elements, right, to frame the global stiffness matrix. If you see the element 1, we have a 64 outside, right, but in element number 2 we have 32. So there should be a divide and multiplication of 2, so that this 32 will become 64, right? So here we are multiplying and dividing by 2, so that this will become 64, and the divided by 2 will get divided by all the elements over here. Okay, so dividing and multiplying by 2 by 2. So we'll have, this will be 64, this will be 64. So this here, the first element will be divided by 2 as well, it will give me 3, and minus 15 divided by 2 will be 15 divided by 2, it give me 7.5, that is minus 7.5, and minus 3. So this is 15 over here, minus 3L is nothing but 15. So similarly here you will have minus 7.5. Okay, in the second row we'll have a minus 7.5 divided by 50 divided by 2 is 25, 15 divided by 2 is 7.5, 25 divided by 2 is 12.5, and minus 3, 7.5, 3, 15 divided by 2 is 7.5, minus 7.5, 12.5, 7.5 and 25. So this is the new one after dividing and multiplying by 2, because why we did is that the outer element of the matrix is 64 and the first element should be same. Okay, now we have divided this. This will be equal to W3, W4 multiplied by W4, W5 and W6. So we have to do the multiplication over here as well. Okay, so what will happen is you have to multiply this minus 1.6 inside that. If you do that, minus 1.67 into 6, so this is minus 10.02. It is if you multiply this with minus 6, 1.67 into 6, we'll get this value. Okay, so I did a mistake over here. It is minus 5 divided by 12 is the value for this is minus 5 divided by 12. It is 0.461, right? So this one is minus 5 divided by 12. Here I did a mistake, sorry. It is minus 0.416, and similarly here also it will become minus 0.416. So if I multiply this with 6, minus 0.416 into 6, it's 2.5 minus 2.496, and again multiply minus 0.416 into minus 5, it is 2.08. Similarly you'll get minus 2.496. Pi, it is minus 2.08. Okay, so we have multiplied those values inside, so this is the value, so it will be plus addition of q3, q4, q5, q6. So here the numbering would be starts with 3, 4, 5, 6, 3, 4, 5, 6, and similarly here also we'll have the numbering 3, 4, 5, 6. Okay, in second element we have addition of one UDL, so we'll have another matrix as well. Okay, now we have to frame global stiffness matrix. We have to frame global stiffness matrix, or else we can say assembly of stiffness matrix, assembly of element matrix equation as well. So here we have 6 nodes. If you see the nodes equal to 6, so the matrices will be 6 into 6. So here 64 will be common outside. So first element, second, third, fourth, fifth and sixth. So 1, 2, 3, 4, 5, 6. So for the convenient, I'm just drawing the line as well. Now we can have we can fill these numbers. So this is the first row, this is the first row and first column. So we have to go to the first element 1 comma 1. So 1 comma 1 is 6. Okay, so 1 comma 1 is 6, and first row second column is first row second column, it is minus 15 3 4. So minus 15 6 and minus 15. So minus 15 minus 6 and minus 15. So 1 comma 6 5 and 6 are 0 0. Okay, so in the similar manner we can fill out all the values as well. So 2 comma 1 would be 2 comma 1 is minus 15 50. So minus 15 50, and 2 comma 3 comma 4 it's 2 3 comma 4. Okay, it's 15 and 25. 15 and 25. So we don't have 2 comma 5 is 0 and 2 comma 6 is also 0. Now 3. So if you see the element, we have the second node is common for both the elements, right? So 3 comma 4 would be common for both the elements. So we have to add this 3 comma 4. The rest w1 w2 5 6 come will be same as it is, but here we have a second node as common. So 3 comma 4 we have to add. So 3 comma 4. So here 3 comma 3. So this element, so 3 comma 1 is minus 6 and 15, 1 and 2, minus 6 and 15, and 3 comma 3. So here we will have 2 3 comma 3s. So here we have a 3 comma 3 6, and here 3 comma 3 is 3. Okay, so it will become 9. So 3 comma 4. So here we'll have 3 comma 4 as a minus 7.5. In the first element we have 3 comma 4 as 15. So minus, and again it will be raised by half, 7.5. Then 3 comma 5 6, you can write straight away these values. Minus 3 minus 7.5. In similar manner you can do the fourth one as well. Fourth row is minus 15, 25, and 15 by 7.5, 75, 7.5, and 12.5. 5 1 0 will be 0, 2 is 0, and minus 3 7.5, 3 7.5. In the last row 0 0 minus 7.5, 12.5, 7.5, and 25. So these are the values after assembling these values. Okay, so this will be into w1 w2 w3 w4 w5 and w6. So this gives equal to, we have a load matrix. Okay, so load matrix is again 1 2 3 4 5 6. If you see over here in the first element we don't have any load, so the numbering, that is 1 1 2 3 4 will become 0 for the first element. Okay, so 1 2 3. So if you see, we have a 3 and 4 as a common element, so 1 will be 0, 2 will be 0, and 3 4 is common for both the elements. Okay, so 0 plus this value. So in first element we don't have any 0, so this is 0 plus this value. Okay, so it will be same minus, so I'm taking it as a minus 2.5, and 4 in 4 also will have the same thing, it is 2.08, and the remaining will be as it is. 5 and 6 would be 2.5 and minus 2.08. Okay, so this plus would be Q1, Q2, Q3, Q4, and Q5, and the last one is Q6. Okay, so these are the values we have to plot now. So if you see, we can apply the boundary condition. We have framed the matrix equation. Apply the boundary condition. So for boundary condition, again we have to go to the figure diagram they have given. Okay, so in this figure, it is the first node is a fixed one, right? The first node is fixed. It is fixed. That means Here w1 comma w2 will become 0. Why? It is fixed, there is no movement, there will be no deflection slope. Okay, and in the third node we have some support. Okay, so we have a support of hinge, it's a hinge support or it's a pin support. Okay, so we can say it is a pin support. So for the pin support, okay, for the pin support or hinge support, the deflection will be 0. Okay, deflection will be 0. So if you see here, we have two numbers, that is w5 and w6. We have to check where is the deflection. So here odd numbers are deflection, that means w5 will become 0. So here w5 will become 0. So we got three boundary condition, w1, w2, w5 will become 0. Okay, so these are the one thing for this thing. So I'll write w1 and w2 are fixed is equal to 0, and w5 will become 0 because it is a pin support or hinge support. In that, deflection will become 0. And now we have to look for the forces, that is shear force and the bending moment. Since we have a fixed support over here, there will be reaction. Okay, so you have to find the q1 and q2. Okay, you have to find the q1 and q2. Here we have to find q1 comma q2. We have to find, it will be question mark. In the pin support or hinge support, the bending moment will be 0. So bending moment, so here where will the bending moment? So bending moment is the even number. So here the bending moment would be 0, that is q6 will become 0. Okay, so in the second node we don't have any this thing values, so it will become, we can take it as a 0. We're not given anything. So for the shear force and bending moment, so q6 will become 0. And since in the middle node, that is the third node, that is q3 and q4 will become 0. Okay, here they are not given any values, so it will become zeros. So by looking at these values, what we can do is we can frame the equation now. If you see, so this w1 is 0, w2 is 0, and w5 is 0. Here in we have to find q1 and q2. q3 is 0, q4 is 0, and q6 is 0. q6 is 0. So these are the values of 0. Now we have to frame the equation. So we don't have to we should not forget that we have a 64 outside as well. So here if you see, we have a 64 outside, so you have to multiply with that as well. So if you see, the first row is 0, so the first row and the first column will be eliminated. Similarly, the second row and the second column will be eliminated because these are the 0 values. Okay, so or else we can frame the equation. If you frame the equation, what will happen? So this row, this element will be multiplied with 0, this will be multiplied with 0. So we have minus 6 w3 multiplied by minus 6 w3, minus 6 into w3, and we have minus 15 into w4, minus 15 into w4, rest all 0. This will be equal to q1. Okay, so because we are dealing with the first row, so this is equal to q1. 0 plus q1, it is q1. And similarly for the second, if you see, the first two element will become 0 and the fifth element will become 0. So we have only these two, 15 and 25, that is w3 and w4. So 15 w3 plus 25 w4, this will be equal to q2. Here why q2? Because again here the value is 0, 0 plus q2 is q2. Now for the third row, so first two element will become 0, 0. So we have this one, this will be multiplied with the w3, 7.5 will be multiplied with w4. So this w5 will be multiplied with this thing, this will become 0, and we have minus 7.56 w6. So 9 w3 plus 7.5 w4 minus 7.5 w6. So this give equal to minus 2.5 plus 0. So that is minus 2.5. The fourth equation, this 2 will become 0, and we have 7.5, 75 and 12.5. Okay, 7.5 W3 plus 75 W4 minus, sorry, not minus, I guess, this plus 12.5 W6. This will be equal to again 2.08 plus 0. It is just 2.08. In the fifth equation, so this will 0 0. So here minus 3 7.5, this will become 0, and 7.5 W6. So minus 3 W3 plus 7.5 W4 and plus 7.5 W6 plus 7.5 W6. So this is equal to, we are dealing with the fifth row, so minus 2.5 plus Q5. Okay, so minus 2.5 plus Q5 it is. Minus 2.5 plus Q5. And the last column, last row, 0 0 minus 7.5 into W3 minus 12.5 into W4 and 25 into W6. So minus 7.5 W3 plus 12.5 W4, then it is 25 W6. This is equal to, so it is minus 2.08 plus 0. It is, the value is minus 2.08. So if you see, again we have to make sure that here we have a 64 outside, so I'm going to write 64 here also. But every equation will have a 64. Okay, so now out of this many equation, first 1 2 3 4 5 6, out of 3 equation we have equal to, after equal to we have some constant. This is this equation and this equation. So we can take this equation and put it in the calculator to get the values of W3, W4 and W6. Okay, so now go to the mode equation for 3 equation and 3 unknowns. We can solve the system for 3 equation and 3 unknowns. So here we have for the first equation, that is 9 into 64, and the second one is 64 into 7.5, and it is minus 7.5 into 64. So this is equal to minus 2.5, the constant. The second equation, so 64 into 7.5 and 65 into 75 into 64. Then after that 12.5 into 64, this is equal to the constant 2.08. And the third equation, the last one, 64 into minus 7.5, this is W3, then 12.5 into 64, then 25 into 64. This is equals to minus 2.08. So if we solve this, we'll get the equation for W3. Okay, for W3, because we solved this 3 equation, in this 3 equation we have the unknowns as W3, W4 and W6. So we'll get these equations only. So W3 gives me minus 1.156 into 10 power minus 2 mm. Okay, so and W4, this is equals to 2.602 into 10 power minus 3, and this is W4 is the radiant, I guess, radian per second. It is a slope because this is an even number. And W6, again we were finding the W6, it is minus 6.072 into 10 power minus 3 radian. Okay, it's not radian per second, it is radiant, sorry. Okay, so these are the 3 deflection and slope. One deflection, W3 is a deflection, W4 and W6 are slope. Okay, so you found out these values. Now what you can do is you can put these values in the this equation. Okay, in the first equation to find out the Q1 and Q2. So if I put the values of W3 and W4, So it is 64 into -6 into -1.156 into 10 power -3 will get the value as 1.9. okay, so here if I put the value for, I'll write down only. So 64 into -6 into W3 is minus 1.156 into 10 power -2 minus of -15 W4 2.06 into 10 power -3. So this is equal to Q1. So I'll put the values. -6 into -1.156 into 10 power -2. Then this is minus of 15 into 2.602 into 10 in power -3. Okay, so this is multiplied by 64. So the value, it is getting it as Q1 equal to 1.941, okay, kilonewton. So similarly you can find out the value for Q2 as well. Q2 equal to, what is the equation we have? 15 W3 25 W4. 64 into 15 W3 plus 25 W4. So let me check the values. So again 15 into W3 is minus of 1.156 into 10 power -2. 15 to 1 point minus right, then plus 25 into W4 is 2.602 into 10 power -3. So this is multiplied by 64. Okay, the value here it is. So Q2, it is a even number, so I guess it is a bending moment. It is -6.934 kilonewton per meter. Meter is a bending moment. And similarly you can find the value for Q5 as well. So this is the value equation for Q5. So it's -3 into W3 is minus 1.156 into 10 power -2. This is -3 into W3 plus 7.5 into W4, that is 2.602 into 10 power -3. Then again plus 7.5 into W6 is minus 6.072 into 10 power -3. Okay, so this is multiplied by 64. Okay, so we got the value as something of 5.5392 into 10 power -1 is equal to -2.5 plus Q5. So we need to find Q5. So Q5 will be equal to, we can take this to the other side. So 5.53921 into 10 power -1 plus 2.5. So plus 2.5. This gives me Q5 equal to 3.054. This is a odd number, that is shear force, that is kilonewton. Force, it is kilonewton. Okay, so we found out all the values of deflection, slopes, and bending moment and shear force. This is the complete analysis of the beam. I hope you understood this problem clearly. So hope to see in the next video. Thank you for watching.